There's a very simple step-by-step process that you can follow to solve a separable differential equation. And if you're not using it, you're probably making those problems a lot harder than they have to be. In my last video, I talked about exactly what this process is. If you want to check that out, you can just go click up there and see for yourself. But I want to show you exactly how to apply these steps to an example problem. So that's what we're going to be doing in this video today, which should be helpful for you to really nail down that topic and do much better at it on your next exam. If that sounds good to you, be sure to stick around to the end of the video. And without further ado, let's jump right into it and I'll show you what I'm talking about. So this first example here, this example does not have an initial condition. So that's something to point out here. Referring back to those steps that we just discussed, the final step is not going to apply because we do not have an initial condition. I do have another example coming up here shortly, which we will get into an initial condition. So you can see one of each, see how those work. So separable differential equation. Obviously, like I said before, the problem doesn't necessarily tell you that it's a separable differential equation. You have to make that determination for yourself based on whether you can get it into one of the two forms that we discussed. In this case, we are given something that is in the form of dy dx equals some function of x times some function of y. So basically we have some function of x times some function of y. In other words, we should be able to just factor this out into something with x's in it times something with y's in it. In this case, that's exactly what we have. So we actually don't have to do any work for the first step of solving a separable differential equation to get it into the necessary form that we need, because the problem gave us something already in the right form. So we already know that this is going to be a separable differential equation because it's already given to us in the form that we want it to be. So since it's already in the right form, what we can do is start separating out our variables, which means we're going to move all of our x terms over to the right, all of our y terms over to the left. So basically we would multiply both sides by dx, and then we would multiply both sides by 1 over y squared, because that's going to cancel the dx's on the left. It's going to cancel the 1 over y squared with the y squared on the right. So we're just going to be left with 1 over y squared times dy equals x times dx on the right. So now we have separated our variables. We've gotten all of our y's onto the left side of the equation, all of our x's over onto the right side of the equation. So once we've done that, what we can do is put the integral sign. That was a sloppy integral sign. Let me try that again. All right, there we go. Put the integral sign on both sides of the equation. So you do need to make sure that you're doing that on both sides. Whatever we do to one side of the equation, we always have to do to the other side of the equation. Okay. Once we have done that, what we can do is just integrate both sides of our equation. So looking at this left side here, we have a dy, which indicates to us that we need to integrate this function with respect to y. We want to treat y as our variable for now, just in this integration step. The dy and the dx are basically just indicators telling us what variable we're integrating with respect to. So this is exactly why we wanted to be able to separate our y's and our x's, because now we have a situation where we're integrating the left side of our equation with respect to y, because we have this dy indicator over here, and the function that we're integrating only has y's in it. So that's super convenient. We're basically treating y as a variable in this case because of that dy, and since there's no other letters besides y, we should be able to integrate this exactly how we would hope to be able to integrate it, just using standard integration techniques. We don't have to worry about treating y as a function because we have a dy here that's telling us to integrate with respect to y. So what we can do is rewrite this actually. Instead of saying 1 over y squared, what I'm going to integrate is y to the negative 2, because y to the negative 2 is exactly the same as 1 over y squared, but it's in a form where we can integrate it just using the power rule. Okay, so the power rule for integration says that we're going to add 1 to our power. So we're going to increase our power from negative 2 up to negative 1. And then we would divide by our new power. Dividing by negative 1 just makes it negative. Once we've integrated, the dy is going to fall off, and then we need to make sure to add our some constant plus c. I'll just call it C1, because when we integrate over on the right side, we're going to do something similar. Okay. So now looking at the right side of our equation here, we have a dx in this case. So that tells us on the right side of our equation only, we are integrating this function x with respect to x. So x is the only thing, the only letter over on this right side of our equation. And the dx tells us that we get to treat x as our variable and integrate with respect to x. So that tells us, again, just like kind of the situation we had over on the left side of our equation, when we integrate the right side, the integral should behave exactly the way we hope it would. We can just use pretty standard integration techniques to integrate this function. Now the integral of just x, we again can integrate just using the power rule. We don't have to do any changes to that function in order to use the power rule like we had to do over here. So I'm just going to kind of copy that right down here, and then let's go ahead and integrate it. So basically having x is the same as having x to the first power. So power rule says we can raise our power by 1, add 1 to our power, 1 plus 1 is 2, and then divide by our new power, which is the same as multiplying by the reciprocal of our new power. So multiplying by 1/2 would be the same as dividing by 2. So we can say 1/2 x squared. And then again, the dx is going to fall off, and we're just going to add in some unknown constant, which we will call C2. So notice we have some unknown constant C1 and some unknown constant C2. What we need to do now, the next step of solving a separable differential equation, is to basically get our y all by itself on one side of the equation, get everything else over on the other side of the equation, essentially. Depending on the context or what you need to use it for, there could be situations where this is actually sufficient, like we really don't need to go further at this point. But let's go ahead and just get y all by itself, just because that's a little bit more convenient in most situations to have it that way. So what we can do first is we can move this unknown constant C1 over to the other side of the equation. Whoops. So we're going to minus C1 from both sides. So that's going to leave us with minus y to the negative 1 equals 1/2 x squared. And then we're going to have C2 minus C1. C1 and C2 are both unknown constants. We don't know what they are, but we do know that if you add two constants together, that's just going to give you some other constant. So this is, instead of writing C1 minus or C2 minus C1, let's just kind of consolidate those two unknown constants into a brand new unknown constant, which we will call C3. Okay. So just kind of something to keep in mind here. Basically, we've kind of arbitrarily decided we're going to use a new constant C3, which is the same as C2 minus C1. Okay. That's not too important because typically you're not going to need to know what each of these constants individually are. But later on, if it were an initial condition problem, we would need to solve for whatever kind of unknown constant we have at the end, basically. Okay. So then what we can do is multiply both sides by -1 in order to cancel out this negative here. So we get y to the -1 equals negative 1/2 x squared. And then what we can do here, we can either say minus C4, or just to keep it easy, having a plus C, we can introduce a new unknown constant C4, which kind of like we did in the prior step, C4 is basically just negative C3. But again, that doesn't really matter. We don't really need to keep track of this over here. That's just kind of me pointing out that we're introducing new arbitrary unknown constants. So we have this new one so that we can keep it as just like plus C, basically. Just keeps it kind of simple. Okay. So then keep in mind that y to the -1 is actually the same as 1 over y. So what we basically can do is basically write, well, there's kind of a couple ways to think of it, but the kind of shortcut way is we can actually raise both sides to the -1 power, essentially flipping both sides of the equation over the fraction, leaving us with y equals 1 over negative 1/2 x squared plus c4. Okay, so now this is a perfectly good place to basically say that we've reached our solution. If we had an initial condition, we would have to figure out what this c4 is here. But in this case, we don't have an initial condition, so we really don't have to worry about it. So this would be our final answer. I'm sure seeing that example helped you solidify the separable differential equation process a bit, but there's other types of examples that this same process can be applied to, and it works out a little bit differently. I have made other videos where I talk about the other version of this process and how to apply these steps to that type of problem as well. In fact, if you click right over there, you can go check out a video where I covered a problem that falls into that other category. Should help you nail down the overall umbrella of separable differential equations, so you'll be ready for whatever your next test throws at you. Go click over there and check it out.